Welcome to Laser Geek. In this video, we're exploring how plasma forms and how it drives penetration in laser welding, photon excitation and plasma formation in laser welding, photon absorption. When the laser beam strikes the metal surface, photons excite electrons in the material. This energy transfer breaks atomic bonds and initiates melting. Plasma creation. As photons continue to be absorbed, the energy density within the weld pool rises to a critical threshold. At that point, the surface metal vaporizes and the gas in the interaction zone ionizes, forming plasma that stabilizes the keyhole and drives penetration. Thickness effect. Thin material. Photons penetrate quickly. The energy density builds fast, and plasma forms almost immediately. Thick material. A larger volume must be excited, so the beam requires more dwell time, meaning slower travel speed, to deliver sufficient energy per unit depth to reach the plasma threshold. Why max penetration fails at high speed? Energy per unit length drops. As speed increases, the joules delivered per millimeter decrease. Keyhole instability. The molten pool doesn't have time to stabilize, so penetration depth collapses. Cross-section geometry. The rectangular laser profile undercuts the far leg of a T-joint when speed is too high, leaving incomplete fusion. Wattage penetration. Raw power only matters if it's coupled with correct speed, wobble width, and focus. Operator grade rule. If speed-rated penetration corridor, you will not achieve full penetration, period. To reach max penetration, tune speed, wobble width, and focal offset to match the unit's wattage rating. For joints thicker than half the wobble length, weld both sides at controlled speed to guarantee full fusion. The thicker is the material, the slower you travel. Laser welding demonstrates this principle with even greater clarity. For example, the IPG LightWeld 1500 is rated for approximately 4 mm penetration under standard parameters. However, controlled field testing has shown that full penetration of 0.25 inch, 6.35 mm, can be achieved in a single pass when the two pieces of material are properly fitted with minimal gap. The applicator lays a bead that ensures complete fusion across the joint. Parameters are tuned to maintain beam stability and heat input within tolerance. A critical distinction lies in weld bead cross-section geometry. Laser welds produce a rectangular or square cross-section, reflecting the uniform energy distribution of the focused beam. Conventional welds produce variable, drip-shaped cross-sections, often wider at the crown and tapered into the root. Heat reality. Even though there's no ground clamp, the weld pool still obeys metallurgy. Too much heat, grain growth, soft metal. Too fast cooling, brittle martensite. Balance is everything. Handheld laser welding balances this issue. Controlled wire feed maintains steady travel speed, and when the process parameters are set correctly, overheating is avoided. Traditional MIG-TIG welders always clamp a ground wire to the workpiece. Laser welders don't. They rely on optics and beam delivery, not an electrical circuit through the part. Novice laser operator one-liner, ground clamp. It's not a ground clamp, it is a safety cable clip. The clip functions as a lockout interlock. If the circuit is open, the gun will not fire. This ensures the tool is used strictly for welding, not as a stray laser sword. Thanks for watching. If you enjoyed the content, please subscribe and give it a thumbs up. I appreciate your support. Got questions? Drop them in the comments. I'll do my best to answer. And if it's a big topic, we might even make a video about it.